Shapes of molecules. How does electrons affect the shape of a molecule? Objectives. Describe the VSEPR theory. Predict the shape of molecules using the VSEPR theory. Determining the shapes of molecules. Lewis electron dot diagrams are two-dimensional and do not show the three-dimensional shape of a molecule. The three-dimensional shape of a molecule is important in determining the molecule's physical and chemical properties. Simple molecules composed of two atoms, such as hydrogen and HCl, are easy to determine. Only a linear shape is possible when there are two atoms. It is much more difficult to determine the shape of molecules made from more than two atoms. Example, carbon dioxide and sulfur dioxide. Both consist of three atoms. While carbon dioxide is a linear molecule, sulfur dioxide is bent. Since the formula cannot provide any information about the shapes, we can use Lewis electron dot structures to help predict the shape of molecules using a model based on the valence shell electron pair repulsion theory, or VSEPR theory. The VSEPR theory. The three-dimensional shape of a molecule is determined by drawing an electron dot diagram and identifying the number of electron groups and the number of atoms around the central atom. We count the following as one electron group: a pair of electrons, a single bond, a double bond, or a triple bond. The valence shell electron pair repulsion theory, VSEPR, is a model that is used to predict the shape of molecules. This model states that electron groups are arranged as far apart as possible around the central atom to minimize repulsion between their negative charges. Lewis electron dot structures are used to determine the number of electron groups around the central atom, represented by X, the number of atoms around the central atom, and the number of lone pairs around the central atom. That's represented by E. Two electron groups, AX2. Central atoms with two electron groups. In the electron dot diagram of carbon dioxide, there are two electron groups, two sets of double bonds to the central atom. The central atom here is carbon. According to the VSEPR theory, minimal repulsion happens when the two electron groups are on opposite sides of the central atom. Here we have an electron group to the left of the carbon, and here you have one to the right of the carbon atom. This gives the carbon dioxide molecule a linear electron group geometry and a linear shape, with bond angles of 180 degrees. When there are two atoms attached and two electron groups, the shape of the molecule is linear. Three electron groups. Central atoms with three electron groups, AX3. Minimal repulsion occurs when the three electron groups are far apart from the central atom as possible, which gives 120-degree bond angles. Here we see the three electron groups arranged around the central carbon atom. This type of electron group geometry is trigonal planar, as in methanol, CH2O. When there are three atoms attached and three electron groups, the shape of the molecule is trigonal planar. Central atoms with three electron groups, AX2E. In SO2, sulfur dioxide, one of the electron group is a lone pair of electrons. Here we have our bond, our second bond, and the third electron group is a lone pair, represented by E. Therefore, the shape of SO2 molecule is determined by the two oxygen atoms bonded to the central sulfur atom, which gives SO2 a bent shape. When there are two atoms attached and three electron groups, the shape of the molecule is bent. Four electron groups. Central atoms with four electron groups, AX4. In a molecule of methane, the central carbon atom is bonded with four hydrogen atoms. From the electron dot structure, one may think the structure would be planar with 90-degree bond angles. However, the best geometry for minimum repulsion is the tetrahedral, which places the 4 electron groups at the 4 corners of a tetrahedron. When there are 4 atoms attached and 4 electron groups, the shape of the molecule is a tetrahedral. Central atoms with 4 electron groups, AX3E. In a molecule of ammonia, NH3, the 4 electron groups have a tetrahedral electron group geometry. However, here we have the 3 electron group and a 4th. However, in NH3, one of the electron groups is a lone pair of electrons. Therefore, the shape of NH3 is determined by the 3 hydrogen atoms bonded to the central nitrogen atom. The shape of NH3 is trigonal pyramidal. When there are 3 atoms attached and 4 electron groups, the shape of the molecule is trigonal pyramidal. Central atoms with 4 electron groups, AX2E2. In a molecule of water, the 4 electron groups have a tetrahedral electron group geometry. However, in the water, 2 of the electron groups are lone pair electrons. Here we have the 2 bonds and the 2 lone pairs. Therefore, the shape of water is determined by the 2 hydrogen atoms bonded to the central oxygen atom. The shape of water is bent. When there are 2 atoms attached and 4 electron groups, the shape of the molecule is bent. Concept check question. Predict the shape of CCl4, carbon tetrachloride. Please pause the video at this time and work this question. Step 1. Draw the Lewis electron dot structure. Here, first we need to count the number of valence electron. Carbon has 4. There's 1 atom of carbon, so we have a total of 4 electrons for carbon. Chlorine, there are 7 valence electrons. There are 4 chlorine atoms, which gives us 28 electrons for a net total of 32 electrons. B. Determine the central atom. Here the central atom is carbon and the 4 chlorine is surrounding it. C. Draw single bonds to the central atom. Here are the single bonds. D. Place all the remaining valence electrons on atoms as lone pairs. We had a total of 32 electrons and we had 4 bonds. So 4 bonds is equal to 8 electrons. 8 subtract from 32 and now we have the remaining electrons to share. Here we have our chlorine receiving those electrons. So the remainder of the electrons are shared around the chlorine atom, the 24 remaining electrons. Finally, turn the lone pairs into double or triple bonds to give every atom an octet, or in the case of hydrogen, a duet. Here, all our atoms are satisfied. Carbon, the central atom, has 4 bonds around it. Each bond has 2 electrons, therefore the carbon has 8 electrons around it. Every chlorine also have 8 electrons around it. It's our Lewis dot structure for CCl4. Step 2. Identify the number of electron groups, atoms, and lone pairs around the central atom. We have 1, 2, 3, 4 electron groups surrounding our central atom. Next, we have 4 atoms surrounding the central atom, the 4 chlorine, which gives us X4. There are no lone pair electrons around the central atom. The formula is AX4, which is a tetrahedral molecule. CCl4 is a tetrahedral molecule. Concept check question 2. Predict the shape of OF2. Please pause the video this time and work this question. And now the solution. Step 1. Draw the Lewis electron dot structure. First, we need to count the number of valence electron. Oxygen has 6. There's 1 atom of oxygen, so we have a total of 6 electrons. Fluorine has 7 valence electrons, 2 atoms of fluorine, which gives us a total of 14 electrons, for a net total of 20 electrons to be shared. Next, we need to determine the central atom. In this case, it's oxygen, with 2 fluorines on the left and right of it. C. Draw single bonds to the central atom. D. Place all the remaining valence electrons on atoms as lone pairs. Here, we used up 4 electrons to make our 2 bond, so we have remaining 16 electrons to share. 2, 4, 6, 8, 10, 12, 14, 16. Next, turn lone pairs into double or triple bonds to give every atom an octet. The fluorine is fully satisfied with 8. The fluorine on the right is also fully satisfied with 8. And the oxygen in the center is satisfied with 8. The 2 bonds around oxygen provides 4 electrons. The 2 lone pairs at the top, 2 lone pairs at the bottom provide the remaining 4. So oxygen is also satisfied. Step 2. Identify the number of electron groups around the central atom and the number of atoms bonded to it. There are 1, 2, 3, 4 regions of negative charges around it. There are 4 electron groups around our oxygen. Next, we have 2 atoms bonded to our oxygen, fluorine on the left and fluorine on the right, which gives us X2. Finally, there are 2 lone pairs of electrons surrounding oxygen at the top and at the bottom. The formula is A, central atom, X2, E2, which is a bent molecule. OF2 is a bent molecule. Concept check question 3. Predict the shape of pH3. Pause the video and please solve this question. And now the solution. Step 1. Draw the Lewis electron dot structure. First, we need to count the number of valence electron. Here we have a total of 8 valence electron. Next, we determine the central atom, which is phosphorus, surrounded by 3 hydrogen. Part C. Draw single bonds to the central atoms. D. Place all the remaining valence electrons on atoms as lone pairs. We have placed 3 bonds around phosphorus for a total of 6 electrons. 8 minus 6 is 2. We have 2 valence electron left to place. We place it around phosphorus. Turn lone pairs into double or triple bonds to give every atom an octet, or in the case of hydrogen, a duet. Our hydrogens are satisfied and our phosphorus is satisfied. Step 2. Identify the number of electron groups around the central atom and the number of atoms bonded to it. Here we have 1, 2, 3 bonds around phosphorus and a lone pair. So we have a total of 4 electron groups around our phosphorus. There are 3 atoms surrounding phosphorus, 3 hydrogens, which gives us X3. And there's 1 lone pair, which gives us E. The formula is AX3E. This is a trigonal planar molecule. pH3 is a trigonal planar molecule.